4.0.0 Transformers. Identify transformers and explain how they operate. Identify the basic components in a transformer. Identify transformer operating characteristics. Calculate turns and voltage ratios. Identify various types of transformers and their applications. Components of a transformer. Basic components of a transformer are shown in Figure 31. The most basic form, a transformer consists of a primary coil, a secondary coil, and a core that supports the coils or winding. So you can take a screwdriver and two pieces of wire, wrap the first piece of wire around the screwdriver, then wrap the second piece of wire around the coils of the first piece of wire. And if you take that first coil and put some alternating voltage on it, 120 volts, you'll get an output on that secondary wire. So here's the core, it's an iron core. Here are the primary windings. There are many turns. Here's the secondary winding. There are fewer turns. This is what would be called a step-down transformer. When you have more windings in the primary than the secondary, your primary voltage will be stepped down. If this is a 2-to-1 ratio, if this has, let's say, 20 turns and the secondary only has 10 turns, then if you put 120 volts into the primary, you're going to get 60 volts out of the secondary. It's a direct proportion. Simple transformer activity is shown in Figure 32. Primary windings connected to a 60 Hz AC voltage source. The magnetic field or flux builds up and collapses around the primary winding. So I believe we've said before that if you take a wire and you move it through a magnetic field, that wire will have an induced voltage and subsequently a current flowing through it. Well, that's the action here. Instead of the wire moving through the magnetic field is moving around the wire. So we have alternating current going through the primary at 60 Hertz, and it creates an expanding and collapsing magnetic field. And that expanding and collapsing magnetic field is cutting the secondary conductors, the secondary of the transformer. And as it cuts the secondary loops, it induces a voltage and a current in that secondary. And depending on how many turns you have in the primary as opposed to how many turns you have in the secondary, you can either step up or step down that voltage. So, all right. 4.1.1 core characteristics are, they're going to tell us about eddy currents, and they're going to tell us about lamination. So I used to tell my students, anytime you see the word eddy currents in the question, the answer is laminated. So, or if you see the word laminated in the question, the answer is eddy currents. So say, why are transformer cores laminated? To reduce eddy currents. Why are motor cores laminated? To reduce eddy currents. Anytime you have a steel core, an iron core, you can get eddy currents in that iron, and to reduce those eddy currents, you laminate it, and that will reduce the surface area where those eddy currents can form. So it says iron core transformers provide better power transfer than air core transformers. A soft iron transformer is also very useful where the transformer must be physically small yet efficient. Laminated steel sheets are often used in a transformer to reduce one type of power loss known as eddy currents. I'm going to highlight eddy currents. These are undesirable currents induced into a circulating around the core. Laminating the core reduces these currents. The steel laminations are insulated with a non-conductive material such as varnish and then formed into a core. So you have a big piece of steel and you would get eddy currents circulating throughout this steel. So they laminate it, they cut it into wafers, and they coat it with a varnish, and then they put it back together with bolts. They bolt through the whole thing, and now the eddy currents are restricted to form in only one layer of the laminate. So the eddy currents are much, much smaller, and there is a much less eddy current loss from that transformer. Transformer windings, here's a highlight. The windings that connected the power source is called the primary winding. The windings in which the voltage is induced and is connected to a load is called the secondary windings. Figure 34 shows a cutaway view of a typical transformer. So in this figure 34, they're showing the cross section of the wires, but that's not what it looks like in the real world. This wire continues out and around and connects here. So these wires are going around and around and around. And here are the primary windings, and here are the secondary windings. So they're actually looped together. Here, they cut this. They took a cutaway view, and the pieces that are wrapping around on this end are not visible. Okay. 4.2.0 operating characteristics. Energized with no load. A no load condition is said to exist when a voltage is applied to the primary, but no load is connected to the secondary. Assume the output of the secondary is connected to a load by a switch that is open. Because of the open switch, there's no current flowing through the secondary windings. However, with the switch open and an AC voltage applied to the primary, there's still a small amount of current called excitation current. So there's still a very small amount of current called excitation current flowing in the primary. Essentially, what this current does is excite the coil of the primary to create a magnetic field. So they're making an electromagnet, basically, is what they're doing. The amount of exciting current is determined by three factors: the amount of voltage applied, the resistance of the primary coil's wire, and core losses, and the inductive reactance, which is dependent on the frequency of the exciting current. Okay. This very small amount of exciting current serves two functions. Most of the exciting current is used to support the magnetic field of the primary. A small amount of current is used to overcome the resistance of the wire and core. This is dissipated in the form of heat, which represents a power loss. So I'm going to say it, there's no such thing as a 100% efficient transformer. They've gotten close. If you have a 2% impedance and you have a 98% efficient transformer, that's a pretty good transformer. If you have a 99% efficient transformer, you've paid a lot of money for it. Instead of doing that, what they usually do is just oversize the transformer by 20%, and they get the power that they need out of it. You don't have to have a 99% or a 100% power efficiency. Phase relationship, it says here, transformers in which the secondary voltage is in phase with the primary are referred to as like-wound transformers. Those in which the voltages are 180 degrees out of phase are called unlike-wound transformers. Dots are used to indicate the points on a transformer schematic symbol that have the same instantaneous polarity. So here's one where they're both wired clockwise. They're both going in the same direction, and the two dots are on the same side of the drawing. This one, the primary is clockwise and the secondary is counterclockwise, and they show that by putting the two dots here. There, that's a unlike wound. So, figure 35b illustrates a transformer in which the primary and secondary are wound in opposite directions. As viewed from above, the primary is wound in a clockwise direction from top to bottom, while the secondary is wound counterclockwise. Notice that the top leads of the primary and secondary have opposite polarities. This is indicated by the dots being placed on the opposite ends of the transformers. Thus, the polarity of the voltage in the terminals of the transformer depends on the direction in which the secondary is wound with respect to the primary. Very good. Turns ratio. There you go. All right. Let's go to our 3D BB. And let's talk about turns ratio. So, I'm just going to draw, and this represents an iron core, in case you were wondering. And then this side is the secondary. So I'm going to say that I have 200 windings, 200 turns in the primary, and 100 turns in the secondary. That's a 200 to 100. They don't write it as 200 to 100. They write it 2 to 1. They always try to make one side equal to 1. So rather than seeing 15 to 2, you probably see 7.5 to 1. Okay. But this is a step-down transformer, meaning that there are more windings in the primary than the secondary. And if we put 240 volts, let me make it red for voltage. If we put 240 volts into the primary, we're going to get 120 volts out of the secondary. So there's a formula that I want you to write down, and I want you to remember the turns in the primary to the turns in the secondary equals the voltage in the primary to the voltage in the secondary. Now I'm going to put current into the mix, but current is inversely proportional. I'm going to put the current in the secondary on the top as opposed to current in the primary on the bottom. So that means that if I have a 2 to 1 ratio and I put 240 volts into the primary, I'm going to get 120 volts in the secondary. And if I put 5 amps in the primary, I'm going to get 10 amps out of the secondary. And look, 5 amps times 240 volts is 1200 volt amps. And 120 volts times 10 amps is 1200 volt amps. Power in equals power out. You don't get anything for free. There's no such thing as a free lunch. That's why the current is inversely proportional. The power we put into the transformer is the power we get out of the transformer. Now, okay, this is purely for learning purposes, but in the real world, you never get quite the same amount out as you get in because of efficiency. Let's say that this transformer was 98% efficient. So if I said 1200, this stupid thing, why are you doing that? Puts the symbol in front of it, and I can't use it. See, why? Why did you do that? There, I'll move over. So if I have 1200 times 98% efficient, I don't know why things aren't working today, times 0.98. Times 0.98. Is it me or is it the computer? I have a feeling it's the computer. We didn't get 1200 volt amps out. We got 1176 volt amps out. That's all I was trying to show you. It took me 17 tries, but we got there. So we got 1170. We got a little bit less out than we put in. And the manufacturers know this. So instead of putting 100 turns in the secondary, they'll put 102. They'll put just a couple more turns in the secondary to make sure that the voltage coming out is indeed 120 volts, and your current's going to be just a little bit less. So that's a step-down transformer. We also have step-up transformers, where if we have a primary of, let's say, 10 turns in the primary and 20 turns in the secondary, we have a 1 to 2 ratio. That means if we put 120 volts into this transformer, we're going to get 240 volts out of the transformer. And if we put 10 amps into the transformer, we'll only get 5 amps out. That's a step-up transformer. Whatever the voltage does, if the voltage steps up, it's a step-up transformer. If the voltage steps down, it's a step-down transformer. All right. And if they said to us we have a primary of 7,200 and the secondary is 240. If we wanted to know what the turns ratio is, we could figure that out by taking, we could either say 7,200 divided by 240, and it's a 30 to 1. Okay, well, that's what we'll do. 30 to 1. There you go. It's a 30 to 1. There are 30 turns in the primary for every 1 turn in the secondary. 30 turns. 7,200 divided by 240. 30 to 1. All right. Back to the book. So here it says the turns ratio is the number of turns in the primary divided by the number of turns in the secondary. Figure 36a, the transformer has a primary winding with 10 turns and a secondary winding with a single turn. That's a 10 to 1 ratio. As lines of flux are generated by the primary expand and collapse, they cut both the 10 turns of the primary and the single turn of the secondary. Since the length of the wire in the secondary is approximately the same as the length of the wire in each turn of the primary, the electromotive force induced into the secondary will be the same as the electromotive force induced into each turn of the primary. So it equals 1 volt. 10 windings, secondary 1 winding. So you get 1 volt. On this one, they're saying you have 10 windings in the primary, and the secondary has 2 windings, so you ended up with 2 volts on the secondary. The transformer in 36B has a primary winding with 10 turns and a secondary winding with 2 turns. Since the flux induces 1 volt per turn, the total voltage across the secondary is 2 volts. Notice that the volts per turn are the same for both the primary and the secondary windings. Since the counter-electromotive force in the primary is equal, or almost equal, to the applied voltage, a proportion may be set up to express the value of the voltage induced in terms of the voltage applied to the number of turns. So here they're saying voltage secondary divided by voltage primary equals the number of turns in the secondary divided by the number of turns in the primary. However you want to write it is fine. I always put the primary on top. Primary, secondary, primary, secondary. They're putting a secondary, primary, secondary, primary. Now, when they start talking about current, we'll see that they're going to have to put the primary current on the top and the secondary current on the bottom. EP is the voltage applied to the primary, ES is the voltage induced in the secondary, N is the number of turns in the secondary, and NP is the number of turns in the primary. So it says, for example, if a transformer has a primary winding with 100 turns, a secondary winding with 50 turns, and 120 volts AC applied to the primary winding, what is the voltage across the secondary winding? So we can just cross multiply. We have the voltage in the secondary over the voltage in the primary equals the number of turns of the secondary divided by the number of turns of the primary. So the secondary voltage equals if they're diagonal, you multiply them. So the primary voltage with the secondary turns divided by the primary turns. And that equals the secondary voltage. They ended up with 60 volts. So here's a highlight. It says a transformer in which the voltage across the secondary is less than the voltage across the primary is called a step-down transformer. Here's another highlight. A transformer that has fewer turns in the primary than the secondary is called a step-up transformer. All right. Types of transformer. Transformers are widely used and to permit the use of trip coils and instruments of moderate current and voltage capacities and to measure the characteristics of high voltage and high current. Since secondary voltage and current are directly related to the primary voltage and current, measurements can be made on the secondary circuits to determine the primary circuit characteristics. Here's a highlight. It says tripping transformers and instrument transformers are examples of this application. So if you have something on the primary that is going to, it'll be a varying current output between 0 and 1,000 amps. Well, your meter isn't going to read 1,000 amps. The wire size for 1,000 amps is huge. It's like 500 kc mil. So instead of using 500 kc mil to try to make the meter coil windings, they're going to use a current transformer. It's going to step the current down from 1,000 amps to 5 amps. So the meter is going to read from 0 to 5 to show us the amount of current in that instrument from 0 to 1,000. All right. So primary or secondary coils of a transformer can be tapped to permit multiple input and output voltages. So here's a multi-tap transformer. We could say maybe this is 120 and this is 208 and this is 240. Who knows? There's a center tapped secondary. This is what you have at your house, 7200 primary and a center tapped secondary with 120 and 120 from the two hots ungrounded going to the tapped conductor or the center tap, which is the neutral. And you can get 240 across the two ungrounded conductors. You can have dual secondary windings that you can wire either in series or parallel. 4.4.1 isolation transformers. Isolation transformers are wound so that the primary and secondary voltages are equal. So the primary and secondary are equal. What's the sense in using it then? For isolation. Here's someone who's not using an isolation transformer and they're standing on a grounded surface and they're touching a metal chassis so that if there's current bleeding off to that metal chassis, they're going to get hurt. They're going to feel it. It's going to go back to ground. Using an isolation transformer, however, isolates that secondary so that if you're touching the metal plate, it doesn't have any path to ground. It's isolated, so you can touch it and not get hurt. Placing an isolation transformer in the circuit interrupts the ground current path that includes the worker. Current can no longer flow from the power supply through the chassis to ground. However, the equipment is still supplied with the normal operating voltage and current. Auto transformers. In a transformer, it's not necessary for the primary and secondary to be separated and distant or distinct windings. Figure 39 is a schematic diagram of what is known as an auto transformer. So it has one coil in common with both the primary and the secondary. So here's the primary voltage across whatever coils you hook them up, and then the secondary can be taken from a common wire between the primary and secondary and a tap conductor that can be moved. You can get whatever secondary voltage you want. Current transformers. A current transformer differs from other transformers in that the primary is a conductor to the load and the secondary is a coil wrapped around the wire to the load. Just as any ammeter is connected in line with a circuit, a current transformer is connected in series with the current to be measured. So here's a current transformer. And it's to an ammeter relay or a controller. Because current transformers are series transformers, the usual voltage and current relationship do not apply. Current transformers vary considerably in rated primary current, but they're usually designed with a turns ratio that delivers 5 amps. I'm going to highlight that. They usually have a secondary that will max out at 5 amps. Current transformers are generally constructed with only a few turns in the primary. However, sometimes they have no turns. The voltage in the secondary is induced by the changing magnetic field that exists around a single conductor. Warning: do not open the secondary circuit of a current transformer while the primary winding is energized. That's definitely a highlight. This can result in a dangerously high voltage being produced in the secondary winding. The secondary of a current transformer should never be left open circuited unless the power source is locked out. The secondary circuit should be closed before power is restored. If you ever remove a meter and the wires are going to a current transformer in a panel, you need to short the secondary side. You need to take those two wires and put them together underneath a wire nut or a lug or something. They need to be shorted. You can't leave them open. I'm not going to read the case history. You can read that. 4.4.4, potential transformer. Remember, potential means voltage. So we talked about a current transformer. Now we're talking about a voltage transformer. It's for instrumentation, the same as the current transformer, but it usually limits the secondary side to 120 volts. The primary of a potential transformer is connected across or in parallel with the voltage to be measured, just as a voltmeter is connected across the circuit. Figure 41 shows the schematic diagram for a potential transformer. So here's a potential transformer. Here's a line, and load is over here. And then you take these two lines going through this potential transformer. The secondary is going to a voltmeter, relay, or a coil. Potential transformers are basically the same as any other single-phase transformer, although primary voltage ratings vary widely according to the specific application. Secondary voltages, secondary voltage ratings are usually 120 volts. Here, and that's a potential transformers. There. And because the output of the potential transformers is proportional to a phase-to-phase voltage of the primary, they're often used to power voltage sensing meters and relays. All right, potential transformer. Section 4 review. Which of the following statements regarding transformer cores is correct? I'll let you decide. On a transformer schematic, dots are used to indicate what? A transformer has 200 turns in the primary winding, 100 turns in the secondary winding, and 120 volts applied to the primary winding. The voltage across the secondary winding would be what? And a voltage sensing relay is likely to be powered by what? Okay, well, this concludes 26201, alternating current. And as always, I hope you got something out of it. If you did, please give me a like and maybe consider subscribing to my channel. And as always, I'll see you on the next video. Thank you. Hey, this is Brian Young. If you liked my video, please give it a thumbs up and consider subscribing. I'll see you on the next video.